of our common logarithms. So remember, common log has a base of 10, and we write it without any 10 on there, so that still means log base 10. And much of this will be done without a calculator. So first one, it said log 1,000. So remembering that that's a base 10. So that means 10 to what power is 1,000. We're looking for the exponent here. So 10 to what power is 1,000. So our answer is 3. Part B, log 1. So 10 to what power is 1? The answer would be 0. And then part C, log of 1/100th, 0.01. So 10 to what power would be 0.01. Encourage you to write that as a fraction. 10 to what power is 1 over 100. So I need a reciprocal, which would be negative exponent. And then 10 squared would be 100. And then estimating. So again, a little bit of number sense here. Log 535. Obviously, if you have your calculator, you can type that exactly in and get the value for that as a decimal. But the idea here is that 10 to the second is 100, 10 to the third is 1,000, and 535 is between 100 and 1,000. So my answer would be between 2 and 3, the exponent on 10. Again, if we make a little list, 10 to the 0 is 1, 10 to the 1 is 10, and 2 is between 1 and 10. So 0, between 0 and 1 would be our answer. And then log 0.5. So if I would think about 1/10 would be 10 to the negative 1, and 1 would be 10 to the 0. So I'm between 1/10 and 1 for my argument of the log. So my answer would have to be between -1 and 0. Again, making a list of powers of 10 would be a good way to kind of think about that one. The next slide here is some review of our exponential, and then understanding that log functions are just inverses of exponentials. So the first directions we were given were to graph f of x. So graphing y equals 3 to the x. Make a table. So here are my table of values. We know what negative exponents do. We know what a 0 exponent does. And obviously we know what just integer exponents do that are positive. So I've got those 5 ordered pairs. I can put those on my graph, and then I sketch, and there's my graph of f of x. List the domain, the range, and the asymptotes of our function here. So the domain, I can use any x that I want. So that's going to be all reals. The range is going to be only y values that are greater than 0. We only have graph up here on the top part of the graph. And there is a horizontal asymptote at y equals 0. And in the negative direction here, I'm getting closer and closer to 0. This is going to keep moving to the right, so there are not any vertical asymptotes. Part C, graph the inverse of f of x. So if I have a table, the easiest way to do that is just switch the x and the y. So that's what I did here in green. So we switch the x and the y, and we put those 5 ordered pairs on the graph, and I sketched that. I kind of crossed over here. That should be hugging the y-axis as it goes down. List the domain, the range, and the asymptotes of my green graph. So the domain, I'm only using x values on this side of the graph. So it's x has to be greater than 0. The range, there's graph down here and graph up here. So I have all reals for the range. And the asymptote is at my line x equals 0. It's that vertical line I'm getting closer and closer to as the x values get closer to 0. And that should not be a surprise as we compare these two. Realize the inverses, we're switching the x and the y, so the domain and the range are going to switch, and the equation of my asymptote is going to switch. Find the equation for this inverse function. So I switch the x and the y, so x equals 3 to the y. And the only way that I can write that if I want to solve for y is to use logarithms. So the exponent is y, the base is 3, and the answer is x. So log base 3 of x equals y. And now that I have it as a y equals, I can use my the appropriate inverse notation. F inverse of x equals log base 3 of x. So that would be the second slide. Next one, we're going to be looking at a situation. We have a common log, which is log base 10. We're now going to be looking at the natural log, which is log base e. You might remember that from advanced algebra. We're going to do a little bit of development of that number e as we go through. So here's the situation. Found a real nice bank that was willing to let me invest $1 at 100% interest for 1 year. So depending on when they compound it, when I get my interest, the value is actually going to change. So this is the compound interest formula. I have some arrows that are indicating what these things represent. P is the starting amount. 1, because I get the money that's in there, I'm still going to get that amount. And then R is our rate as a decimal. N is the number of compoundings that are done each year. That appears twice in our formula. And T is the number of years. So in this particular case, I'm investing $1. So 1 is the P, 100% interest. So 100% as a decimal is going to be 1. So R is a 1. It's for 1 year. So T is going to be a 1. And what's going to be changing is my red is the N value. So if they are compounding that annually, so one time each year, that is a 1 as well. So I actually have all ones in there. And as I evaluate that, I end up with $2, which makes sense. If I get 100% interest on $1, I'm going to get a full $1 more. So we end up with $2 at the end of the year. If it compounds semi-annually, which means I'm going to get some of my interest after 6 months. So that means I'm going to earn a little bit of interest on my interest the second half of the year. So I actually get a little bit more than that $2 because for the last 6 months, I'm earning some interest on the interest from the first 6 months. So all that changes here is this N value. So I put in a 2 and a 2. Again, evaluate, parentheses first, take that to the second power, and then we're multiplying by 1, of course, which doesn't change. So I get $2.25. Well, what if I want to get my interest quarterly? So now I change the N to a 4, and I get $2.44. This is a pretty good plan. I'm getting more money as I compound more. So monthly, plug in 12, even daily, 365. At the end of each day, I want that little bit of interest that was earned, and I end up with $2.71 at the end of the year. So I'm doing quite well compared to my $2. So you might think about, well, what's happening to this particular number? Is it heading off towards infinity? Is it heading off towards 3? Is it heading off towards pi? What is the number that I'm heading towards? Is this going to go on and go up forever? Well, I have another table here that actually breaks it down after every day. What if we did it every hour, every minute, and every second? We realize there really isn't much change in the value of how much money I'm going to get when we go from hour to minute and second, even though this number gets really, really big. So it must be approaching some value. So this is the definition of Euler's number. It is E. You can find it 2 different places on your calculator. Second division or second ln, and then you raise that to the first power. And Euler's number, there's an approximation. It looks like it might repeat. It actually does not repeat. It's irrational. It's a number very similar to pi in that sense. And here's the definition. It's the limit as n approaches infinity of 1 plus 1 over n to the n, which really sets up from what we just did up here. Our value was a 1 out in front, so we didn't have to worry about that when we multiplied by 1, so that's gone. And it was over 1 year, so it was n times 1, so we didn't have to worry about that. So we got rid of those ones, and there is our definition of Euler's number. So that number is used a lot in continuous growth situations. So we also use that with logs. So that's called a natural log. So our next slide, go through that. So log base e of x is the same as natural log of x. So when we see ln, that means base e. So as we're starting these out, I would encourage you to just write that in there so you realize that e is the base. Just like on the first questions of today, 10 was the base when it was a common log. When it was log, without anything else written. All right, so without a calculator, let's see if we can find these. Natural log of 1. So e to the what is 1? That would have to be 0. Part B. Natural log of e to the 6th. So when I put this e down here, it reminds me it's asking e to what power is e to the 6th? Well, what would make this true? The only thing that makes this true is if my question mark is a 6. So this answer would be 6. Natural log of e. E to the what is e? Well, that would have to be a 1. And part D, e to the what is 0? Can I take e to some power and have it equal 0? Remember, e is a number, if I were to estimate it, is around 3. So 3 to some power equals 0. That's never going to happen. So that is undefined. So we cannot have an argument in here that's 0, and we cannot have an argument in here that's negative. So a couple of requirements there that we would have to have, and we're thinking about what type of answers we can have when we have log equations. This in here cannot be a negative, and it cannot be 0. All right, so instead of using that formula from before, now we have what's called our continuous change formula. So we have a of t equals t is our time, a is the amount that I have after t years, p is the starting amount, so that's our principal amount, e is our number e now, and r is the rate as a decimal. Don't be confused by this. R, do not add a 1 to it. That's a common mistake that students make. If it says 5% interest, the rate is going to be 0.05. The E value is going to make this thing increase without anything being adjusted with the R besides just changing it into a decimal. So that's all that you have to do, change it into a decimal and plug in that particular value for the R. All right, so we got an example here. Population of New Zealand in 1992 was 3,381,000. The average annual growth rate was 1.3%. What was the population predicted to be in the year 2010? So let's think about what these values are going to be if we assume annual growth, if we assume continuous growth. So some things that won't have to change. T is our time. So I'm going 18 years, so T is going to be 18. R, our rate as a decimal. So move the decimal point 2 places because it was percent. So 0.013. The principal amount, so the starting amount in this case, is 3,381,000. And the N, if we're talking about annual growth, the N is going to be 1. So we can plug those in that formula that we had at the beginning. Evaluate, make sure that you use parentheses on this exponent. I would just probably type it to the 18th power. And I end up with 4,265,944 people. If we assume continuous growth, the P value is still the same. The R value is still the same. The T value is still the same. We just use this formula instead. And we could have predicted we do end up with some more people than we had in the other situation with the other formula. So 4,272,382 people if we assume continuous growth. So when we're looking at the question, we need to figure out which formula should we use. And there's a word that's going to help us figure out which one we should be using, the continuous idea. All right, so then what tip to use the number e in our work? That's going to be continuous. Log graphs are inverses to what type of functions? Linear, no, power. I had some students think power in the past. Remember, power is like y equals x to the third. So the inverse of that is y equals x to the 1/3. So that is not log. Trig graphs, no. Exponential and log graphs, those are the ones that go together. We did that last time, and we did that today as well with the y equals 3 to the x. And remember, the answer to a logarithm is the exponent. So we're looking for what is the exponent, and hopefully it becomes pretty simple for us once we consider that. We're just looking for an exponent. So that was our day 2 slideshow.